Hi, welcome to the STOR 155 lecture on confidence intervals on section 5.2. And really the words confidence interval should be here on this slide as well, so I'll add them. And giving this lecture, I'm assuming you read section 5.2, and I'll present a couple of examples here and then leave you a couple of problems to work, and in class on Monday, we'll discuss those. Okay, so here's the idea. So we've learned lots of theoretical material so far in the class, and we're finally ready to start doing something with our statistics. So the idea is we're going to start with an example where we're a company, and we're testing a new cholesterol drug. We'll call it LDL be gone. Now, you don't have to worry. You're in your teens or 20s, and you don't worry about LDL and the difference between LDL and HDL. But we want to decide whether we should spend $1 billion to develop this new drug, LDL be gone. And our question is, does the drug work? We want to decide, does the drug have a causal effect on the level of cholesterol? Well, you know well from the class that to establish causation, we want a well-controlled experiment with a control group and experimental group. We found 100 volunteers with high cholesterol. They have cholesterol around 150, and we randomly assigned them to a control group and a treatment group. And we note that the 50 in the treatment group have a reduction in total cholesterol from around 150 to around 135. Okay, and but this is the result of one experiment. Before we spend the $1 billion as a company developing the drug, we want to know could this effect have happened by chance? Okay, so what's the probability that a group like this had a big reduction in cholesterol by chance in a study where we had 50 in a control group and 50 in a treatment group? And in this class, we're going to have two ways to study this, okay? The two ways that we're interested in. Today, we're interested in confidence intervals. And later, we're going to study tests of significance, or also called hypothesis tests. But you could ignore that bottom half. Today, we're focused entirely on confidence intervals. That is, we're trying to guess a true population parameter mu. We never know the population mean, okay? We have a sample mean x bar, and we want to try to get an idea of where mu should be based on where x bar is. And we're going to use the fact that a sample mean x bar makes a very good unbiased point estimate for mu, but our question is, how close is x bar to mu? Okay, this is sort of what we're trying to get at. And that way, we can say where we think mu is. And we won't be able to say an exact value for mu, but we're going to find an interval where we think mu is located. Okay, so we'll start by talking about the theory a little bit, and then we'll go right into an example. Okay, so here's the idea. We assume our population is normal. We know that won't necessarily need to be true in the future, but right now we'll assume the population is normally distributed with mean mu and standard deviation sigma. Okay, and we take a sample of size n. And when I translated these notes from PowerPoint to what I needed for this presentation, explain everything, some of the x bars got lost, so I need to write in an x bar here. So the population mean is mu, and we have a sample of size n with mean x bar. We don't know mu, but we're going to use x bar to try to predict where mu is. But we know from our study of the sampling distribution that the distribution of x bar is normal, and that the standard error of x bar, or we could think of it as the standard deviation of x bar, is the population standard deviation divided by the sample size. Okay, now we know for normal distribution that the probability is that any observation is within 2 standard deviations of the mean. This 2 is actually an estimate, but the bottom line is our confidence interval for where mu is going to be this x bar we observe. So x bar is going to be our best guess at mu. It's going to be right in the middle of our confidence interval. And we're going to guess that mu and x bar are about 2 standard deviations apart. Okay. Now that 2, the 2 we've been using for a 95% confidence interval, that's actually what was an estimate when we were using the 68, 95, 99.7 rule. And a truer number is 1.96. Now I wrote here the true number, but actually 1.96 is also an estimate. It's just a much better estimate. So we're going to guess that mu lies in the interval from the x bar we observe down to 1.96 standard deviations and up 1.96 standard deviations. So our 95% confidence interval is just going to be that mu lies between x bar minus 1.96 SE sub x bar, or sigma over square root of n, and x bar plus 1.96 times SE sub x bar, or sigma over square root of n. So we want to be really comfortable with both these notations, that they represent the same thing. Okay, and basically, this is sort of the first major takeaway for what a confidence interval. What makes it a 95% confidence interval is that we use the numbers 1.96. And we know if I make a picture of a normal distribution, say the distribution for Z, standard normal distribution, that 95% of the observations lie between 1.96 and negative 1.96. Okay, so to summarize that, the 95% confidence interval is going to be the set of values from x minus 1.96 standard errors to x plus, that should be a plus, to x plus 1.96 standard errors. And we believe with 95% confidence that mu lies in that interval. And we'll talk about what I mean exactly by 95% confidence in a few slides. So more summary. Okay, so this confidence interval, the width of this confidence interval is 2 times this number 1.96, because we're going from x bar minus that to x bar plus that. Half the width of that interval is called the margin of error. And since we use 1.96, the number for 95% of the values being in that range for the standard normal distribution, 1.96 times the standard error of x, half the width of the 95% confidence interval is going to be the 95% margin of error. Okay, that's lots of explanation. Maybe an example would be helpful. All right, so we're going to try to estimate what the average age mu is of school students in the United States. And we're going to suppose that we don't know the mean mu, but that we do know the population standard deviation. Okay, now that's kind of odd. You may say, well, how can we know the population standard deviation if we don't know the population mean? But let's put that concern aside for a minute and assume we do have some way to know the population standard deviation. Okay, excuse me, we take a sample of size 100 from the population of students. We can assume it's a simple random sample. And we get that the average age, it turned out to be exactly 11.0. Okay, 11.0 is then our best guess for the population mean of all students in the United States. But we can't say it's exactly 11. We assume it's somewhere in a range around 11. And we're going to try to find a 95% confidence interval for the true mean of age, the true mean age of school students in the United States. And we know that that 95% CI, so this is the 95% confidence interval, that it's our observed sample mean x bar minus 1.96 of those standard deviations of x bar, SE sub x bar, or sigma over square root of n, up to x bar plus 1.96 sigmas over the square root of n. Okay, so, and notice x bar, our point estimate for mu, is right in the middle of this confidence interval. It's our best guess at where mu is. It's our best estimate. It's an unbiased best estimate, actually. Okay, so to find that confidence interval, I put in the quantities I know, 11 minus 4.6 over square root of 100 times 1.96. I should have probably written the 1.96 first to be consistent. Up to 11 plus 1.96 times the same thing. 4.6 over square root of 100. Luckily, square root of 100 is something we can do in our head, right? So if you do the calculation there, you get that the confidence interval, so the lower half is 10.0984, but I'll just go to one decimal place. Let's say 10.1, because it lets me make a nice observation here. If I know the left half of the interval is 0.9 less than x bar, then I know even with without doing the calculation that the right half of the confidence interval has to be 0.9 to the right of x bar, because I know x bar is right in the middle of the confidence interval. Okay, so that's no coincidence. 11 is right in the middle of this confidence interval. And when I say we're 95% confident that mu, the true population mean, mu should be in this interval. Mu should be in this interval. And when I say I'll write this down this will be written in a slide or two. But when I say I'm 95% confident that mu is in this interval, I mean that 95% of the time I take a sample of size 100 and calculate the confidence interval this way. I'll get lots of different confidence intervals for lots of different samples, but 95% of those confidence intervals will contain mu. So I'm 95% confident that mu is in there. All right, that's example 1. Okay, so just to summarize, I'm saying that the interval from 10.1 to 11 is 11.9, sorry, is a 95% confidence interval for mu, and we know that the margin of error, so it's still 10.1 to 11.9. I broke these slides apart oddly here, and the 95% margin of error, it's half the width of that confidence interval, so it's got to be 0.9. Or if you wanted to calculate it, the margin of error, the 95% MOE, is equal to 1.96 times standard error sub x bar, or sigma over square root of n. Okay, I just think of it as half the width of the confidence interval, less to memorize. All right, now statisticians get quite hung up on what I mean by 95% confidence interval. They like to say, statisticians, that they don't mean that the probability is 95% that mu is in here. Okay, so we have to be really careful to say that when we say 95% confidence interval, we mean that 95% of the time I take a sample of this size and calculate the confidence interval in this manner. Mu will lie in the confidence interval. Excuse me. Okay, and that's summarized here. All right, let's try another example. I want to see the effect of sample size n on the width of the confidence interval. So here, it doesn't say exactly what we're trying to estimate the mean of, but we're told that the population standard deviation is 18.3. And we've taken a sample of some size, either 50 or 500, and we found in either case that our sample mean was 48.3. And I just want to calculate the 95% confidence interval for the mean for where mu is based on each of these sample sizes. And I'll do A on this page. I'll do B on another page, and then I'll summarize them on a third page, and we can talk about how they're related. Okay, so first of all, for that for the 95% confidence interval with n equal 50, we know that the 95% CI goes from x bar minus 1.96, standard error sub x bar, up to x bar plus 1.96, standard errors. Okay, so that's just, maybe I'll write down below where I have a little more room. This is just x bar minus 1.96 times 18.3 over square root of 50. And this time I'll actually write what x bar is, since I have it there, 48 up to 48.3, which is still x bar, plus 1.96 times the standard errors of x bar. So 18.3 population standard deviation divided by square root of 50 again. Okay, I'll let you do the calculation, but after a little bit of rounding, I get 45.9. And now you can do the calculation or not, but you should be able to say right now what the upper bound is. Since 45.9 is 2.4 below x bar, the other endpoint of the confidence interval should be 2.4 above x bar. So 2.4 above x bar is 50.7. And if you do the calculation, which I'm sure you will, I trust you to do that, you'll get 50.7 for the upper bound. So with a sample size of 50, I find that I'm 95% confident that the true sample mean mu, I don't know where it is somewhere in this interval from 45.9 to 50.7. Okay, let's see the effect if we got the same sample mean with a sample of size 500 instead of size 50. So I'll do that here. Here I'm going to concentrate on part B. And same as before, it's x bar minus 1.96 standard error sub x bar, but this time the standard error is sigma over square root of 500, up to x bar plus 1.96 times sigma over the square root of 500. Okay, I do that calculation. So if I do x bar minus 48.3 over square root of 500, I got 47.5. We could do the calculation for the right endpoint, but we know we can see this is 0.8 below x bar. So the right endpoint should be 0.8 above x bar. So let's see, that should be 49.1. Okay, and I assume with 95% confidence, same confidence interval, that mu is in this interval. Okay, on the next slide, I'm going to summarize what the two confidence intervals were, both 95%, to see the effect of increasing n on the width of our confidence interval. And remember, the narrower our confidence interval, the more precise our estimate. We have a tighter guess for mu. Okay, so I'll just remind you, with a sample size of 50, we got a confidence interval of 45.9. We were 95% confident that mu lay between 45.9 and 50.7. When I used n equal 500, I got a confidence interval of 47.5 up to 49.1. Okay, so we can see larger sample size, larger n, leads to a narrower CI, a more precise confidence interval. Okay, so narrower, smaller, however you want to put it, a narrower confidence interval or a lower margin of error. Okay, and this makes sense. Remember, we've studied variability is less. Variability of the sample mean is less for larger samples. We expect larger samples to give more precise estimates. We expect our estimate for where mu is, here I have it trapped between 47.5 and 49.1, to be narrower than the interval we got for 45.9 to 50.7. So I'm just going to draw on the number line how this looks. 48.3 is in the middle of both intervals. Maybe I'll use the full range of color available and explain everything here. So first, I'll draw the 95% confidence interval with sample size 50. So this is 45.9 up to 50.7. And then for n equals 500, for a larger sample size, I have a very tight range here from 47.5 up to 49.1. Okay, so this is n equal 500. And then the large sample here, the larger interval here, sorry, smaller sample is for n equal 50. So increasing our sample size leads to smaller confidence intervals. Both confidence intervals are 95%. We're 95% confident in each case that mu lies in the corresponding interval. Both confidence intervals are centered at x bar. X bar is always our best estimate of the sample size mu, our unbiased best estimate. All right. So we may want to ask, now we've said 95% confidence interval so far, and we've gotten hooked on this number 1.96. But depending on our application, we might want a 99% confidence interval if we're dealing with something in medical care. If we're dealing with something in finance and investments, we might be perfectly happy with an 80% confidence interval. We would make plenty of money if we could say with 80% confidence what a return on some assets is going to be. So a natural question for us to ask is, okay, this is the margin of error for a 95% confidence interval, and that was because if I look at the standard normal distribution, that's the normal distribution with mean 0, standard deviation 1, then 95% of the time, 95% of the values lie between z equal 1.96. We've used 2 in the past in class, but today we revealed the truth that it's actually 1.96. And that is the appropriate, this is called z star, that's the appropriate z star for a 95% confidence interval because 95% of the values lie between z equal negative 1.96 and z equals 1.96. So a natural question to ask is, what if I wanted some other level of confidence? Like, what if I was interested in an 80% confidence interval? What should the 80% margin of error be? And to answer that, we basically look at a standard normal distribution, okay, centered at 0, standard deviation 1. And now we're trying to find the z star. So here's z star, here's negative z star. We're trying to find the value that has 80%, the values of z star, negative z star, so that 80% of the distribution is between z star and negative z star. Now, we've done exercises like this in the past. At the time, you may have wondered why we were doing them. This is why. And we know that I need to find z star so that 10% of the values are to the left of negative z star. We know exactly how to do this, right, with norm.inv. So this means negative z star is equal to norm.inv. In other classes, they may use table A for this. You know we don't use table A for anything, like what a Neanderthal activity, right? Norm.inv of 0.1, and it's a standard normal distribution, so 0 and 1. And if you do that, when I did that calculation, which I carefully wrote down on this page, I got negative 1.28 is that number, so Z star. Instead of 1.96, we're going to be interested in going 1.28 standard deviations either way. So we'll see that result on the next page. The work I've done down here is going to disappear, and we're going to see the end result. Okay, so take a mental snapshot of this. Okay, and we can see the result is when I want to do an 80% confidence interval, I go 1.28 standard deviations either way. So we're not memorizing the number 1.28. We're not interested in that. There's nothing special about 80%, but this would give us, this means that the 80% confidence interval, 80% CI, would just be from X bar still in the middle, always our best guess, down 1.28 standard errors, and X bar plus 1.28 standard errors. Okay, that's the idea. And I think what I'm going to do now, this lecture's reached 21 minutes, and I've been told these lectures should never go over 20. So what I'm going to do, I'm going to leave 2 examples here for you to work. We'll work them in class. Please indicate with the thumbs up or thumbs down buttons if this was worth doing. You can watch this video as many times as you like. It'll look good in my count of views, okay, on YouTube. But I mean, with exercises to do. Take out, first is this summary page. If you wanted any level of confidence, we just did C equal 0.8. This picture is a lot to explain in a video. I'll talk about this in class, but this is basically about how to get the Z star, the critical Z value for making a confidence interval of any level of confidence. And then I'm just going to leave you these 2 examples to look at. So example 3, sample size 500 for both. You're going to find a 95% confidence interval and a 99% confidence interval for where mu is. This is going to involve the exercise of finding the appropriate number of standard deviations. It's not 1.96 or 1.28 to go each side for a 99% confidence interval. You already know how to do 99% confidence interval. And then there'll be a last exercise just practicing finding these critical values Z star for C equal 90% and C equal 85%. Okay. This completes the lecture. Okay, work the exercises, indicate whether this is worthwhile or not with thumbs up or thumbs down. This may affect, how we do some future classes, because I've noticed the class time where we spend discussing problems on the homework is very useful for some, less useful for others. And I want to decide, should we be spending that time primarily for lecture? Should we be doing some problems, do some lecture outside of class? You can let me know your thoughts in the comments. Okay, very, very polite thoughts, please. Okay, all right, thanks. See you in class on Monday. I hope you have a great break.